Our first speaker is Carl Malings.
All right,
and just
thank you.
Tell me next if you have more than one slide.
Yeah, will do. So yeah, previous slide, please. So I'll today be briefly summarizing my recent work, which is where we looked at how to combine air quality models, outputs, and satellite retrievals together to improve air quality forecasting at various spatial scales. And this work was done in collaboration with people listed on this slide, working at the Global Modeling and Assimilation Office, or GMAO, at the NASA Goddard Space Flight Center, and also was supported by a NASA postdoctoral fellowship program. So next slide, please. So in this work, we wanted to demonstrate how, by combining different sources of air quality data together with some fairly straightforward methods, we would be able to create more accurate combined forecasts of air quality at regional to sub-city scales. You can look at more details of this in the paper, which is cited on the slide here. But for now, I'm going to highlight some of the results for forecasting in the New York City area, which is one of the areas we looked at in this paper. So I'm showing the results in terms of the NO2 surface concentration forecasts and their correlation with actual measured surface concentrations in the area on the left-hand side, and the root mean square error of those forecasts on the right-hand side. So the basic result of here is that while the global atmospheric chemistry model, in this case, we're using the GMAO's GHGSat model system, was the main underlying driver of the forecasting method we used, the satellite data, in this case from the TRPOMI instrument, did play a key role for the spatial downscaling of the model data. And the ground-based measurements were also important for providing both bias correction and for incorporating information about spatially and temporally local pollution events. So we also saw that the performance in general of this proposed method was relatively good overall, and across lead times compared with the other methods using subsets of the data sources, either only the ground data or only the model data or some limited combination of model and satellite data, which are the other colored lines indicated in the figure here. Next slide, please. So building on that, yeah, thanks. So building on that, I'd like to briefly highlight some preliminary results regarding how these combined estimates might be used together with low-cost air quality sensors, which often require locally relevant calibration. So in an experiment, we used a combination of data sources, as I discussed previously, to provide an initial estimate of the regional air quality. And then we used a network of EPA regulatory monitors in the area as a stand-in for a low-cost sensor network. And because we trust that the regulatory monitors are accurate, we therefore know that when we try to calibrate these to a regional estimate, for example, using a linear regression approach, we know what the result should be, namely a slope of 1 and an intercept of 0, which is shown as the ideal target result in the figure here. So by applying some filtering based on correlations between the measurements and the estimates, we were able to develop the network level calibration indicated by the blue marker here, which was pretty close to that ideal result. And this indicates that the sort of regional air quality estimates I discussed previously could be a useful tool for in situ calibration of low-cost air quality sensors, which are an emerging tool for communities to monitor their local air quality. So I think I'll sum up there and move on to the next talk, I guess.
Hi, everybody. Can you hear me?
Yes, we can.
Thank you. This is Jessie from University of Iowa. So today we're sharing some of our work to improve surface PM2.5 forecast the next day through a bias correction framework. First, I'd like to acknowledge NASA and NOAA for funding this research, as well as all the co-authors for their contribution to this work. So here we have developed a multi-model, multi-AOD ensemble bias correction technique through the use of different chemical transport models and different satellite AOD products, as well as ground observation. So we have developed this bias correction technique in a two-part study, and both parts have been published. So in the first part, we only use the ground observation of surface PM2.5 and a model forecast surface PM2.5 to improve the forecast for next day. So as you can see from this scatter plot, the top right one, so the first row shows the raw model simulated surface PM2.5 compared with the ground observation, and the bottom row shows the common filter, the bias corrected surface daily PM 2.5. So we can see there's a significant improvement in the forecast daily PM 2.5, and also overall the ensemble shows as the bottom right also give the best results. Then in part 2 of the study, we add the satellite data, especially focus on areas where ground observation of surface PM 2.5 are not available, such as rural areas. And then we do a bias correction again to forecast the surface PM 2.5. So in the bottom right, the scatter plot, again, the top row shows the model simulated a raw daily PM 2.5 compared with ground observation. And the bottom row shows the forecast corrected daily PM 2.5 for next day. Again, we can see an improvement. So far we have focused this bias correction techniques in the continental United States. And our next step is to apply this technique in Alaska to improve the fire forecasting of smoke. So that's all I have.
Okay, well, if we don't have any questions, I'll move to the next speaker, April.
Well, hello everyone. I am Huanxin. You could also call me April. Previously, I studied satellite remote sensing of cloud and aerosol at the University of Wisconsin-Madison. And now I'm a postdoc using satellite data and statistic models to assess the influence of climate change issues on human health. Well, as you know, wildfires has caused a range of health impacts, ranging from direct thermal injuries to chronic lung disease. And the situation is getting worse as climate change is creating hotter and drier conditions in many parts of the world, increasing the risk of wildfires. So I'm currently working on developing a long-term high-resolution wildfire indicator from 2001 to 2021. This kind of information will not only benefit the research community, but also provide required information for health professionals and policymakers to advance our response to climate change. So in general, the indicator is built based on satellite observations of active fire spots and clouds and modeling estimates of global population. This is an example result showing the difference of annual mean number of persons exposed to wildfire by country between 2001 to 2004 and 2017 to 2021. This map indicates that about 2/3 of the world countries had an increase in wildfire exposure, which are colored in red and orange, and the largest increases were observed in Congo, India, and Mozambique. But this indicator is not perfect because while I was calculating the influence of cloud on wildfire observations, I only considered the total cloud fraction, which is not accurate enough. As you may know, the effect of thin clouds like cirrus and thick clouds like stratocumulus on spaceborne wildfire observations are totally different. So in the future, I will improve the wildfire indicator with cloud type information from active sensors, such as radar and LiDAR observations from CloudSat and Calypso. And besides that, I will also work on improving the model resolution from 10 kilometers to 1 kilometer. Well, that's all I have. Thank you so much for your attention.
Okay, well, thank you very much. I think we're going to move to our next speaker.
Hello, everyone. My name is Alqamah Sayeed, and I'm a postdoc at STI USRA, Huntsville, Alabama. And today I'm presenting research by my group in which we estimated PM 2.5 concentration at various US embassy locations through a machine learning approach. Can you move on to the next slide, please? So the objective of this research was to develop a machine learning model to estimate hourly PM2.5 concentration at specific location for having a temporal data set of 21 years. For this, we used MERA2 assimilation, MERA2 assimilation from NASA Goddard as input. It consists of various metrology and aerosols. And then the output for the model was the surface measurements from various monitoring sites from various US embassies. So can you move on to the next slide? Here I'm presenting some results. Although I have results for 70+ embassies, but I chose my hometown, which is New Delhi. Also because it has a high variability of PM2.5 and very very poor air quality during winters. As you can see on the left panel in the first plot, there is a scatter plot which shows the observations and prediction on X and Y axis. And you can see there is a very close agreement between the observations and predicted or estimated PM2.5. The R-square was 0.94 for the whole data set. In the next panel shows the air quality index for different seasons. DGF is winter, MAM is spring, JJ is summer, and so on is fall. You can see that the air quality is pretty bad during winter and spring seasons. When we look at the long-term trend or annual trends, we can see there's almost a straight line and there's no variability. But when we zoom in through the seasons in the right-hand panel, which shows the seasonal trend of different for the different years, we can see that there is a slight increase in the seasonal trend from 2000 to 2020. There is an increase in the PM2.5 concentrations, but there is also a decrease during the summer and fall, summer and spring seasons. So the key takeaway from this research was that a consistent time series data at temporal resolution of every hour, every day, every month, and every day was created for more than 70 embassies in US embassies. And this data set can be used to assess air quality and its impact on human health. So that's all I have for today.
Great. Well, thank you very much. That was wonderful. Okay. We will move on to our next speaker, Diana Guzman Barraza.
Hi, everybody. Thank you for joining me here on this talk. My name is Diana Guzman, and I'm a senior consultant at Carbon Limits, an international firm based in Oslo, with many years of expertise working on addressing climate change mitigation, and specifically, which is what I would like to share with you today, addressing methane emissions in the oil and gas industry. Next slide, please. So as you know, it is quite urgent to take action on methane emissions, and a lot of countries have joined in the fight, as announced in Glasgow last year. So this is good news for everybody. And next slide, please. And at Carbon Limits, we have been working on methane emissions over 10 years, including in 20 countries at an economy-wide level, trying to help the parties to the UNFCCC convention, or the governments or companies also in an economy-wide scale, 20 countries having analyzed by Carbon Limits, which is very strategic intervention. Next slide, please. And at the global level, we have also been working supporting the OGMP partnership, the oil and gas methane partnership, developing the technical guidance documents, and these are at an industry level. So this is basically helping the entire industry in the world, the entire oil and gas industry in the world, to address methane emissions. And next slide. At the company level, we are also developing tools, so helping companies address their emissions and move forward. Next slide, please. So all of these guidance and plans and interventions, all of these require a number of projects and considerations, of course, but in all of them, satellite images are present, because it's a unique and very valuable tool to help decision makers identify missions, and civil society also to have a way to transparently observe what's going on, and the regulators to observe compliance one day. And everything focuses on methane emissions. So this is why satellite observations are really important for addressing climate change. Next slide, please. So the best approach is combining a series of tools, not only satellites. So this is only one of the tools in the toolbox, but certainly a very valuable one. And the best combination is having a top-down approach combined with the bottom-up approach. Next slide, please. So from this experience, taking public and private databases from satellite missions in the world, some of the key takeaways we would like to share with this group today and discuss, of course, later. We are available to further discuss these issues. So we would like to share that this is definitely a global solution for a global problem, but it is not the only one, not the only tool. Next slide, please. And it is definitely not a silver bullet, because there are still some performance issues and there are challenges that we still need to address, but they are extremely useful one way or the another, and certainly will be part of the road forward. So building competencies and understanding of the capacities and the challenges of this tool in the industry at the government level and at the corporate level, and in the civil society as well, is extremely relevant to address climate change the way we need to. So next slide, please. With this, I appreciate your attention, and I reiterate that we are open for partnerships and for future work on this. We have ongoing work, and we would love to further discuss your projects and opportunities. Thank you, Jenny.
Thank you so much. So much enthusiasm there. It's great. Okay, so we'll move on to our next speaker.
Hi, everyone. I'm Lingzhi from the ICCT. We are an independent research organization that provides technical and scientific analysis to environmental regulators. In this talk, I'll share some highlights of our study last year on assessment of air quality and health impacts of heavy-duty vehicles in G20 economies. So this study covers every G20 economy, their diesel HDV exhaust emissions, exposure, health impacts, as well as climate effects. In this talk, I'll just show one aspect of the results, total NOx emissions. Next slide, please. So a quick overview of the scenarios. We incorporated 5 scenarios into our analysis. Adopted policy scenarios includes adopted policies up to the end of 2020. The second scenario, expanded road class, assumes G20 economies implement Euro 6 equivalent standards by 2025. The third one in green here adds accelerated fleet renewal to the previous scenario. The next scenario, next generation standards, builds upon adopted policies and Euro 6 standards and assumes all G20 economies implement next generation standards by 2030, with a 90% reduction in NOx emissions compared with Euro 6 equivalent levels. And the last scenario assumes accelerated fleet renewal policies on top of next generation standards. Next slide, please. So as shown by the yellow line on the left figure, expanded implementation of Euro 6 equivalent standards in all G20 economies by 2025 would reduce NOx by 32% over the next 2 decades compared with 2020 levels. And next generation standards could reduce NOx by 71%. Both figures for all G20 economies on the left and for the US on the right show that next generation standards are key to sustaining NOx emission reduction. As you can see that only the bluish lines keep decreasing in the next 2 decades, while in other cases, vehicle growth outweigh the effects of policies in later years. And in addition, implementing fleet renewal policies on top of Euro 6 equivalent standards and next generation standards can accelerate emissions reduction by 5 to 10 years. Next slide, please. So finally, some high-level recommendations that we share with regulators are implement Euro 6 equivalent emission standards in all G20 economies no later than 2023 to 2025. This could avoid 580 billion in health damages from 2020 to 2050. Develop stringent next generation standards and introduce this in all G20 economies. This could avoid 5.3 trillion in health damages. Complement next generation standards with zero emission vehicle policies and accelerated fleet renewal to further increase health benefits. Though fleet renewal is not a substitute for tightening new vehicle standards. Last but not least, for countries that allow import of used vehicles, tighten new vehicle standards and require used imports to meet equivalent standards. That's it. Thank you.
Thank you very much. We'll move on to our next speaker.
Jenny, thank you so much. Hello, everyone. My name is Eric Choi. I'm Director of Business Development at GHGSat. I'm very pleased to be here, and I'm particularly pleased by the ordering of the speakers because Diana, just 2 speakers ago, enunciated far better than I can the importance of both methane and the utility of satellites in quantifying methane emissions around the world. That's precisely what we do. So we currently have 3 satellites in orbit. They're named Claire, Iris, and Hugo, and this is an expanding constellation. We've got our next 3 satellites scheduled for launch later this year in the summer. They're named Penny, Luca, and Diaco. And if you're wondering where we get the names of our satellites from, they're actually named for the children of our employees. So it's just like a little small reminder of the importance of what we're trying to do for future generations. Now, what's unique about our satellites compared to the plethora of other satellites that are up there is our capability at a very high resolution, sub 30 meter spatial resolution, to quantify methane emissions at point sources. So what this means is that we can attribute sources down to individual facilities. And this is something that you can see in the image in the top right there, which is an emission from a landfill in New Jersey. So this is sub 30 meter spatial resolution and with a detection threshold on the order of 100 kilograms per hour. Now, what Diana also touched upon, entirely correct in saying so, is that, of course, satellites are only one of a number of tools in a tiered approach that we could take to quantifying point source methane emissions. So complementing our satellites, we actually have 2 aircraft-based sensors that have been deployed across North America. And these sensors, you can see an example of an observation on the bottom right there. That, I believe, is a compressor station in the Permian Basin. The aircraft that we have basically an order of magnitude improvement from the standpoint of spatial resolution and detection threshold. So about 1 meter resolution and about 10 kilograms of methane per hour. So about an order of magnitude better. And what is really important and special that this opportunity to speak to you today is we're very keen on growing our partnerships with the scientific community. So we've had an ongoing collaboration for a number of years with ESRON, for example. This is the Dutch Space Research Institute, precisely in the manner that Tracy talked about this morning, the complementarity of public and private sector satellites. So with ESRON, we basically tip and queue with data from TRPOMI looking at the wide scale, and then we kind of zoom into those point sources a bit like a microscope, if you will, at that sub 30 meter level. Barry Leffer mentioned this morning that we are currently in the on-ramping process for the NASA commercial small-sat data acquisition program. And depending on the outcome of that process, we hope to be able to offer our data to the wider US scientific community as early as this year. So maybe I'll just flip to the last slide here, which is that's not quite the, sorry, previous last slide. Just a bit of a case study, if you will, of some work we did in Bangladesh last year. We were tasked following detection of an elevated emissions from a European Space Agency satellite to look at a landfill outside of Dhaka, the capital of Bangladesh. And as a result of that, the government in fact struck up a committee to look at these results and find ways of potential mitigations for this situation. So that concludes my talk. Thank you so much for this opportunity. I'll be around tomorrow for the virtual networking. I'll be happy to take any questions that people might have. Thank you again.
Okay, I think, thank you very much. That was great. I think in the interest of time, we'll just move to our next speaker, who I've seen her name already pop up twice this meeting. So looking forward to this.
Thank you. Hi, everyone. My name is Madankui. I'm a PhD student at Columbia University. It's a great pleasure today to give this flash talk on analyzing ozone formation chemistry during summertime pollution events. And before I start, I want to thank everyone for making this possible despite all the challenges. And also want to acknowledge the help from all the names listed on this title slide. Next slide, please. For this work, we use tropospheric vertical column densities of formaldehyde and NO2 as a proxy for VOC to NOx ratio to indicate ozone sensitivity to its precursors. We want to specifically understand how ozone precursors, which are formaldehyde and NO2, and ozone production regimes, which indicated by their ratio, vary on ozone exceedance versus the non-exceedance days. We first sorted out days when the MD8 ozone is greater than or equal to 71 ppb, which we define here as ozone exceedance days, following the 2015 NOx ozone standard, and mark those days in light beige. And accounting for data quality leaves us 19 out of 22 exceedance days with TropoMe data available in New York, which is the study region. And then we mark those days in darker orange. Finally, we match up the non-exceedance days and mark them in blue. So what we do is to composite those days for the TropoMe data and calculate the average, which are shown as this panel on the right side. So we have formaldehyde and NO2 and their ratios averaged on 19 non-exceedance days on the right, on the left column, and averaged on the 19 exceedance days on the right column. We find an increase in formaldehyde densities about 75% on the exceedance days, and a smaller increase in column NO2, about 4% over this region, but especially in the New York City urban core. Next, for this comparison specific, sorry, go back to the previous one. So for the bottom row we see here, the increase in formaldehyde dominated this overall changes we observe in the ratio. We can identify this spatial tightening of areas with lower formaldehyde to NO2 ratio on the polluted days. So next slide, please. We also look at the surface formaldehyde. This figure I show is a distribution of surface formaldehyde measurements at the EPA ORD Westport site, averaged on the exceedance days. Still the 19 days I showed earlier, the exceedance days average in orange and the non-exceedance days in blue. The surface formaldehyde is higher on the exceedance days, with the mean value increased about 4 ppb on the exceedance days, which agrees with what we see from the satellite. Next slide, please. We also examine the variation in tropospheric vertical column densities of NO2 using these measurements from the Pandora spectrometers for the hours surrounding the TropoMe overcast time, which is around 1:30 p.m. local. So I show here only Rutgers shows a drop in the NO2 columns on the exceedance days, but all the other sites, the ones in this New York City urban core and the ones along the Connecticut shoreline showed an increase in NO2, which actually also generally agrees with the satellite, but we see more of the finer scale spatial variations. Next slide, please. With this, I want to conclude my talk, but I'm happy to discuss any of this either here or offline. Thank you so much.
Thank you. All right, so here's the last speaker that I have slides for. Priyanka, take it away.
Thank you. Hi, everyone. I'm a newly minted assistant professor at UC Denver. And today I want to talk to you about the study in which I looked at the impact of air pollution on infant mortality in India. And I think this is the first national scale analysis that attempts to do so. And I specifically examined how sensitive this estimated impact of air pollution was to two different remote sensing derived exposure assessments. Next, please. So the data that we used actually has come from the National Family Health Survey. It's a national representative household survey, which consists of 2 steps. One is clusters or villages or census enumeration blocks are sampled from all 640 districts in India, and then households are randomly sampled from these clusters. All women in these households aged between 15 to 49 years of age are asked questions about the children that they have. And specifically, the births and deaths are recorded. And the outcome I consider in this study is infant mortality or death of a child in the first year of life. The other sub-outcome is neonatal mortality, which is death in the first month of life. And in total, we found that there were 210,430 children who died in the first month of life in this sample. Next slide, please. So we assigned exposures to every child using these 2 exposure data sets. You can see that there are slight differences. The one on the left is from Washington University. The one on the right is from IIT Delhi. The bottom figure shows the difference. And so you can see that there are spatial differences between these two data sets. Next slide, please. The 2 data sets also show sort of different temporal patterns. You can see sort of what sort of an annual average, what sort of a monthly average cycle looks like on the right for different states. When I looked at correlations between the 2 data sets by states, we found that they most disagreed for union territories in India. Union territories are really, really small, so it's perhaps not surprising that for those few grid cells, we see differences in the 2 exposure assessments used. Next slide, please. So given these spatial and temporal differences, we wanted to understand how sensitive the health impact assessments were. And so in this study, we controlled for various child level, mother level, and household level characteristics. We also controlled for residual spatial confounding by using district fixed effects and residual temporal confounding using fixed effects for year of birth and state month to account for seasonality. Next slide, please. So to sum up, we basically found that both exposure, we actually found consistent results from both exposure assessments. Both exposure assessments showed that exposure to PM2.5 in trimester 3 in the first month of life of the child was significantly associated with higher odds of infant mortality, and most of the impact of PM2.5 on infant mortality was seen in the first month of life, which means that we really have to protect children in the first year in the first month of life from PM2.5 exposure. Next slide, please. So to conclude, we need to protect children in the first month of life specifically because they're vulnerable to air pollution. And we found robust results across model specifications and exposure assessments. This paper came out a few days ago, and you can read the entire analysis here. Thank you.
Thank you. Okay, so those are all the speakers for whom I have slides for. I'm not sure if Amit or Emory have been able to join. Alex, did you hear back from them?
I didn't hear anything from them. And I don't see them in the attendees, so I don't know.
Well, in that case, we can open it up for questions from anyone, and we have some time for that. So I'd actually like to ask, a number of you brought international perspectives, and particularly a couple of you talking specifically about India. And I was thinking, you know, from our perspective, many of our researchers are based in the US, working with NASA, you know, US public satellite data, but how do we sort of bridge that gap and think about working with partners, stakeholders, and what might be something important to consider that you've noticed in your work? That's open to anyone who wants to answer.
I just want to mention a new satellite that to be launched. Maya will have focus on India and on the area on the house and the aerosol pollution. So that'd be maybe something interesting.
I guess I'll mention briefly, we did specifically choose to use a globally available, the GHGSat model, which is a global model as opposed to a regional model, with the view to extending the same procedure out to other countries without having to change models. We haven't done that yet, unfortunately. It's still on our to-do list, but that is sort of a choice we made when starting the project.
Anybody else want to speak to that question, or we move to another one?
Yeah, I think in the India project, we actually found that because of a dearth of ground-based monitors, especially in rural India, the satellite estimates of PM 2.5 were really had a high degree of uncertainty. And so although there are these amazing global products available and they can be used for countrywide analysis to really look at anything on a finer scale in these parts of where there are sparse monitors, there's just a greater need for ground-based monitoring.
Okay, we have a question from Tracy, a question for Diana and Eric. How do you think methane connects or should connect with air quality products like NO2 and SO2? How are applications or stakeholders related or different? Should a future applied science team have more methane emphasis? What do you see as the main communities needing the data? So thinking for the fourth HAQAST team in the future, perhaps.
Diana, did you want to get started? Well, maybe I'll say a few words then. And this is going to be a bit of a cheat because it's sort of turning the question around. Is, myself, I'm an engineer and not a scientist, so really, we want to listen to you in the community as to, what is the need and what is the research requirements that capabilities such as ours in the private sector, might be able to support. Certainly the initial interest, of course, was methane being such a potent greenhouse gas, but more to the point of this particular audience being one of the precursors to ground level ozone. And of course, at the end, those two things are coupled in the sense that climate change and hotter weather and stagnant air tends to exacerbate the effects of ground level ozone. But ultimately, you're the science community. We're all ears. Please tell us what we can do to help you.
Well, since I asked the question and Eric pushed it back, I'll just say, Diana, I don't know if Diana's there, if she wants to weigh in at all. But I think, to me, one of the things we've gotten a lot of interest in methane from the same stakeholders that we work with on an air quality side. I mean, state agencies, cities, the EPA. So I think that there's overlap in the stakeholders that we've seen, but I bet that there's a lot of other stakeholders that are interested in methane who may not be interested in air quality. And so I think, to me, the connection is kind of from a multi-pollutant control perspective, but that's how it looks from the air quality side. And it may look different from the climate side, for example.
Okay, well, great to start thinking about that. I think methane is definitely becoming a bigger and bigger issue. Unless someone else wants to comment, I'll move on to the next question. Is there any work being done using indoor air quality measurements or wearable sensors to augment satellite measurements, especially for validating exposure or health impacts? So if anybody wants to comment on their work or particularly good examples of this that they would like to talk about. I can repeat it one more time. I don't, this is just if anybody's working with indoor air quality measurements or wearable sensors, something that helps with the satellite measurements when you don't have as much ground monitors. And Tracy, you showed up again if you want to comment on it.
Well, I'll comment, but I feel like I don't want to. I've spoken a lot today, so I don't want to take the airtime from our panelists. But I'll just say we often get the question about indoor air quality because, from a health exposure perspective, people spend more time than outdoors. So, and the idea that a lot of emission sources that are outdoor, I mean, that are indoor may affect the outdoor, and et cetera. But right now, I'm not aware of any integrated monitoring that connects indoor air quality and outdoor air quality and satellite data. I mean, those are really, for the most part, they're very different communities that work on indoor air quality and outdoor air quality. It tends to be more meteorologists that kind of come into the and environmental science folks on the outdoor air quality side, and more building engineers on the indoor side. But I think there are like snippets of connections, and I think it would be an exciting area to expand further, especially if you look at areas in the developing world where indoor air quality is a huge source of pollution affecting the outdoors. So I think it's a very nice question, but I'm not aware. The short answer is there anything? And I've never heard of it.
Yeah, I'll maybe briefly add on tangentially. Before this project, I was working with low-cost sensors for air quality. And with those, there's a lot of emphasis on using them both indoors and outdoors. Again, I don't know, like you said, I don't know of any efforts to connect those back to satellite data, but maybe the low-cost sensors, in some cases, the same type of unit is used both indoor and outdoor. Maybe that's a link that could be used to then connect the indoor to the outdoor and then to the satellite data. I don't know of any current efforts in that direction.
I think we have a good research project.
Okay. Well, we got a comment from Emory who wants to thank you all for such a diverse array of talks. And I'll second that for sure. And then we also have a specific question from Juan to Priyanka. How close or far grid / measurements of PM 2.5 with respect to families were they surveyed?
Yeah, so for every every household, we knew which village or a village in rural areas or census enumeration blocks in urban areas. We knew where each child was born, and the lat long of the center of these clusters is available from the National Family Health Survey. For privacy reasons, the clusters are sort of displaced by a maximum of 5 kilometers for urban blocks and 2 kilometers for rural blocks. So we basically constructed, buffers of 2 kilometers and 5 kilometers around each sort of grid point, and assigned a spatially weighted exposure from this 1 kilometer by 1 kilometer grid to the specific cluster in question. I hope that answers your question.
Oh, can I ask a general question? Okay, like for me, I'm at an early career stage. I'm a scientist. How to connect with stakeholders? For example, I have an exposure model about wildfires, how to work with stakeholders or how to find the stakeholders to work with. Yeah, I'm asking this because I'm preparing a proposal. Yeah, thanks.
Yeah, I mean, I guess I'll, hi, April, and nice to see you. And it's nice to see a lot of familiar faces in this lineup. You know, I think that, first of all, that's a challenge for a lot of people. And I think it's becoming more of a challenge as applied sciences has more money, that there's more funding opportunities from applied sciences, but they require stakeholder partners. So I think there's an incentive, and I think it's a healthy and good incentive provided by NASA to be building these relationships, but there's often no framework for what that means. And so, I mean, I would just say, one thing I would do is either, I think there's sort of two basic approaches. One is you either think about who is your dream stakeholder in the sense of, if you're studying the Pacific Northwest, maybe your dream stakeholder is the Washington State Health Department. I mean, if you sort of think about from a topic and from a region, who your dream stakeholder is, and then try to figure out how to get from where you are to that person. And, this could be, talking to people in your network. Have you ever done any work with Washington? Do you know anybody there? But it could also even be something like LinkedIn, where you will put in the name and then see, do you know anybody who works there? And this is similar to networking for a job or anything else. And I'll just say, as an example, I put in a proposal recently, and I wanted to work with somebody doing environmental justice in Wisconsin. So I talked to our state health department, and I was talking to someone who I didn't know that well herself, but I just said, we'd like to work with some environmental justice groups in the state. Do you know anybody? And she said, oh, yes. And she introduced me, and it was great. We had a lot to talk about, and it worked out well. I think another approach, though, is to start where you already have a connection. So, and if maybe your dream is to write a proposal for Washington State, but you don't know anybody there, and maybe you do know somebody in Wisconsin or in Georgia, where you're already working and have a network. So I think that then, I think sometimes we're sort of looking for that kind of perfect stakeholder, when really the perfect stakeholder is the person in our community that we can meet with for coffee and, be engaged with on a local basis. Those are my two answers.
Okay.
Other people should chime in.
Mm-hmm.
Does that seem, as an early for you, right, April, does that seem like a strategy that do you feel like makes sense as an early career person? Or are there other this is, I think, a topic that a lot of people struggle with at every career stage.
Mm-hmm. Oh, thank you so much for suggestions. I will try them.
I just also want to pipe up and say, feel free to reach out with me if you want some help connecting, especially with anybody who's talked at the meeting or anybody on our team. I'm happy to help do that. We also have a HAQAST LinkedIn that you can be a part of. And, we're happy to help if, you have a particular project. Sometimes people email us to say, hey, can you advertise this in your newsletter? We're happy to help try and make connections in different ways, because that is a really important part of this team, is really helping build those connections to help our researchers and our stakeholders. So please, let's chat, and that's an open invitation for anyone.
Yeah, and actually, I think thanks, Jenny, that's really the best advice. But just I think with a couple of thoughts, just as you're doing this, I think it's easier for us to connect if you send something like, I'd like to connect with a stakeholder in the West or the East or on air quality. Sometimes people say, we want to connect with a stakeholder. And that's something we can't reach out to somebody and be like, somebody wants to connect with a stakeholder. But so if you give us just a little bit to work with, then we can start doing the matchmaking more effectively. And I would say a second thing that I would recommend thinking of before you reach out to the stakeholder is, what are you offering them? And, you know, this could be money. And I think if you're willing to write somebody in funded as a partner on your proposal, then I feel like you can reach out almost to anyone, anywhere. Or if you already have money and you're reaching out to offer them free help, like that's another context that sometimes comes up. But I think that you want to be careful about, if you're getting all the money for yourself, but you're asking them for help, then I think it's a little bit more of a delicate situation. And I think it's something that maybe you might want to question whether you could fit them into your budget, because typically, like, you might not want to spend a lot of time on something that just took your time and didn't give you anything. And these busy partner organizations certainly, I think, feel the same way. And I think that came up in the Q&A during the environmental justice session this morning, about the fact that, you know, these environmental justice groups in particular may not have a budget at all for air quality. So if we want them to work with us on satellite data, then it's really essential to pay for their time as well.
Thanks.
I actually have a question for Lingzhi Jin. I don't know if I'm saying that right, but I really loved your slides and the way it was presented. It had a really nice policy feel, and I'm kind of wondering, like, how you came up with these policy scenarios, because it really seems like they're very actionable the way you laid it out.
Thanks, Jenny, for your question. So basically, we're a very policy-focused organization, but it's like enabled by data analysis and research. Our goal is to influence policies. And I get the feel that this group is very focused on like satellite monitoring data. I myself is in atmospheric sciences major previously. But now, I'm not sure if everyone knows that, like, currently for the G20 economies, not every country is, has adopted like Euro 6 equivalent standards, which is the world-class standards right now. US is at Euro 6 equivalent. China just became, they adopted China 6. India adopted BS6, but there are countries that are not at this level yet. If they do that, they would contribute to like emissions reductions a lot. And then the next level is like California, California's low NOx omnibus regulation, which is like the next generation standards. So we're just thinking, okay, so what if the G20 economies adopt next generation standards in the next, I don't know, like 8 years. So that's the thinking there, and it's almost like they are going to do this anyway. It's just a timeline. Like if we really do want to, protect our environment and fight against climate change, then we will have to move to more stringent emission standards and zero emission vehicles. But when you do that, it's gonna make a lot of difference.